All right, hello everyone. Welcome to today's lecture. This is the fifth lecture in the YEA F equals MA lecture series. And today we'll be talking about work and energy. All right, so let's do a quick introduction. What is work and what is energy? In short, work and energy are very important concepts. And I have some sort of definitions here. They might seem a bit circular, but work is the energy transferred by like a force. If you apply a force over a distance, then you will be doing work. And energy is the capacity to do work. And what makes this useful, as you will see later on, is conservation of energy. So energy will be conserved in closed systems. And so we can use that to skip, sometimes we can use that to skip a lot of computation and get the answer quickly just by using conservation of energy. All right, so let's first talk about work. Yeah, work is, as I said, is the energy transferred by a force, and it's a scalar quantity. And what it's equal to, well, work is equal to it's equal to force times distance. Or in terms of vectors, it will be the dot product of the force and distance. And yeah, so why do we define it like this? Well, kind of makes, if you have a force this way and you're pushing a box that way, well, you're going to be doing some positive work. You're just pushing the box is going where you want it to be pushed. And so you're doing work. Now, what if instead of this, you're pushing the box this way, but the box is moving that way? I'm not sure why. Maybe there's some other force on it. Well, then you're sort of slowing the box down. You're doing negative work here. So work is a scalar quantity, but it can be positive or negative depending on like whether you're applying force against the particle's motion or in line with the particle's motion. All right. And I know we briefly mentioned dot products in a previous lecture, but just to review, the dot product will be equivalent to FD cosine theta, where theta is this angle here. It's the angle between the force vector and the displacement vector. All right. Oops. Yeah. So it's also in this diagram here. Um, we'll have to multiply by the cosine of theta because we only want this component of the force that's in the same direction as the displacement. All right, let's do some examples. So I'll give you, this one should be pretty quick. I'll give you a minute to do this. Just check if you remember. Oh yeah, in this case, first we're considering first the case where it's in the same direction as the displacement. So yeah, some people have answered. To find the work here, we just take FD and then cosine theta. Well, theta is just 0 in this case. Cosine 0 is just 1. So we have 10 newtons times 5 meters, or 50 Newton meters. And Newton meters, the SI unit for this is also called the joule. So the work done is 50 joules. Okay, but what happens if the force is applied at an angle of 30 degrees? Now, what is the work? I'll give you a minute to do this. All right, yeah, a lot of people have answered. So in this case, well, there's not a lot we have to change. It's just that this 0 is now a 30. All right, so we'll have 50 cosine 30, which should be 25 or what? Which should be 25 root 3 or 43.3, I'm pretty sure. All right, so that's our answer here. Okay, that's fun. But now I also want to mention what happens when the force is not constant. So in this case, we'll have to use a bit of calculus to find the total work. And what we do is we have our small work element is going to be the force dot a small distance element, right? So we're going to take the integral um and get that the work is just the integral of the force dot some displacement vector. And this probably won't show up too often on the F equals MA unless it's asking you to integrate a graph, which you should, I guess I'll talk a bit about that. So yeah, this integral you'll sometimes see as you get a graph. Um, you get a graph here, and this is force, and this is X, and I don't know, some shape here, like that. And you want to find the total work done? Well, that would just be this area over here. And yes, I have another example. So some of you have already answered, but I'll give you a few more minutes to do this. Okay, yeah. So for this, we just have to use like our formula, and we will get that the answer is just equal to this integral, which should be 8 joules. All right, let's do some more examples, and I'll give you a few more minutes for this, and these are actually pretty important. You will see them later on. Oh, um, sorry, number one should be asking for the work. So what is the work that you need to compress the spring? All right, it's been a few minutes, so let's go over this. Yeah, number one should have asked for the work. So, hmm, actually, let me go over number two first. So for number two, seems pretty straightforward. You have here, there's a block, and there's going to be gravity that's acting it on it. And gravity near the surface of the earth is always mg downwards. All right. And this block is raised a height h. And since our force is gravity, right? And gravity is always mg downwards, so it's constant. So we can just use the formula work is force times distance, which is going to be, in this case, negative mgh, since it's going opposite to our displacement. So yeah, when we raise the block up, gravity will do negative work. Okay, now number one. Um, so for this, we have a spring right here. And it has a spring constant of K, and we compress it a distance X. So we want to find the work required to do so. Well, this example is slightly trickier because the spring force actually varies with distance. If you remember from last lecture, the force given by a spring is negative kx. This is Hooke's law. All right, so if we displace it by some x, there's going to be a spring force this way. That's kx. So what we have to do is we have to apply kx of force to keep it in this position. So what we're going to have to do is to use the fancy integral formula and get that the work is the integral from 0 to x of kx dx. So this is 1/2 kx squared. All right. So it's very nice. And you will see these later because these are basically just potential energies for these two forces. All right, let's go on to the work energy theorem. So let's define the kinetic energy of a particle as half mv squared. What the work energy theorem says is that the change in kinetic energy of our particle is going to be equal to the work done on the particle. So if we have a particle here and we do some work on it, we apply some force times the distance, we do some work. What we're going to get is that the kinetic energy of the particle, which is half mv squared, is going to be equal to the work that we did on it. So, and this is the change in kinetic energy. So if it starts with no kinetic energy, then that's just the kinetic energy. But if it starts with some kinetic energy, then it will increase by W. And this is very cool because now we can solve for the velocity right here. So if we know the work, we can find the velocity. So let's do some examples. Let's do first number one. See how we can use the work energy theorem. So I'll give you a few minutes. As always, if you have any questions, you can ask me or send your answers in chat. Oh wait, and before anyone asks, I forgot to specify the mass of the particle. Um, okay. What's a good mass here? Let's say the mass is 0.2 kilograms. All right. So it's been a while. So I will first go over number one and explain a bit more on how to do this. So first of all, we have a particle here, and it's moving with a velocity 5 meters per second. So what's its initial kinetic energy? Well, its initial kinetic energy, half mv squared, was half times zero point 0.2 kilograms times 5 meters per second squared. And this is equal to 2.5 joules. All right, so that's our initial kinetic energy. Um, so how will we use the work energy theorem to find our final kinetic energy? Remember, we can just say the work is the change in kinetic energy. So what's going to happen here is, well, first of all, what's the work that's done? Well, the work is going to be the force times the distance. That's 10 newtons times 1 meter, or 10 joules. So our final kinetic energy is going to be our initial kinetic energy plus the work that we did. That's how much it changes. And this is 12.5 joules. So that's our final kinetic energy. And now this is why we wanted to do this in the first place. We want to find its final velocity. So how do we do that? Well, we can just use 1/2 mv squared is equal to the kinetic energy, which is equal to 12.5 joules. So 1/2 times the mass, 0.2 times v squared equals 12.5 joules. And we will get that v is equal to 5√5 meters per second, or approximately 11.2 meters per second. And that's our final velocity. So now I hope you will have some idea on how you would approach question 2 and also question 3. All right, so it has been a while, and so I will start going over these problems. Yeah, I did make some slight modifications, but all right, let's start with number two. Um, so number two is similar to number one, but actually it's also slightly different, and you will see why as we go on doing this problem. So what we have the same mass as in problem one, and it's traveling with a velocity of 5 meters per second, and it's 0.2 kilograms. All right. And in problem one, there was a force of 10 newtons this way. And that was fine. We could just use conservation of energy to find its final velocity. But now what happens when the force is 10 newtons this way? Well, let's see. So remember how we did number one? We first started out with the kinetic energy. The initial kinetic energy is 1/2 mv squared. And I think we calculated this to be equal to 2.5 joules. All right, that's very nice. Now, the next step is to calculate the work. The work, all right, it's FD cosine theta. Last time, theta was 0 because they were in the same direction. This time, theta is 180 degrees because they're in opposite directions. So cosine theta will become -1, and this will become -10 newtons times 1 meter, which is -10 joules. All right. And the third step we did last time is kinetic energy, the final kinetic energy. We have the initial kinetic energy plus the work. What does this give us? 2.5 joules plus our -10 joules of work is -7.5 joules. All right. But wait, hold on. This -7.5 joules, that's equal to 1/2 mv squared. Our mass, we know what our mass is. Our mass is 0.2 kilograms. And v squared is always positive. So how are we getting a negative number here? Well, it turns out the reason is that the work really isn't -10 joules. And what's happening here is, first of all, let me erase this. What's happening here is that the ball's going to slow down and eventually stop. And after the ball stops, the ball will turn back this way and keep on going that way. And what happens now is that the force, the 10 Newton force, is in the same direction as its motion. So if we go back to our problem, it says travels a distance of 1 meter. What really happens is that the ball, well, it will get stopped before it even travels 1 meter. So I guess we couldn't find its final velocity at this point. But what we might want to do is say, okay, this distance it travels this distance plus this distance is 1 meter. Then what will be its final velocity? Well, at this point, its kinetic energy will be 0 because the work done will be 0. So what we can do is we can try to find this point, first of all. We're going to have a kinetic energy is half mv squared, which is 0. So then the work we must have done to get to this point would be negative 2.5 joules. All right. And if this is equal to negative force times distance, that would mean that the distance we traveled is 0.25 meters, 25 centimeters. So we're going to turn back after we've gone 25 centimeters this way. And what's the rest of the work going to be? Well, the rest of the work is going to be positive because now the force is in the same direction as our displacement. So the rest of the work is our 10 newtons times there's going to be 0.75 meters left to go if we're traveling a total distance of 1 meter. Oh, I'm sorry about that. Let's do this. Okay, cool. Can you see it now? All right. Thanks for letting me know. Okay. And they probably want to move this over a bit. All right. Do you want me to? Okay. Basically, what happened there is we basically, if you do the work, so the final kinetic energy at this point will be 0. So we can use that to find the work that we would have to done to get to this point. And if we set that equal to the force times the distance, we will get the distance to this point, which is 0.25 meters. So the rest of the work is going on 7.5 joules. And now we can actually find the final velocity. 7.5 here. And we should get root 75 meters. Oops, root 75 meters per second. And it will be backwards, so I guess negative. Which is around 8.66 second, and it's that way. All right. So now let's go on. Oh, let's go on to number 3 now. All right, this is a very similar problem. What we have is an object of mass 2, and it's on the floor here. And what's going to happen is there's going to be a gravitation force and a normal force, of course. But there's also an applied force of 10 newtons. And we're also going to have a frictional force that's this way. All right. So what's going on here? Well, first of all, we know that the normal force has to balance out gravity. So it's just mg in this case. as it normally is for a box sitting on the floor. Now, if you remember from last lecture, our friction force is going to be mu k times our normal force. And this is just going to be mu k times mg. All right. So now we know all the forces on our object. We want to find the final kinetic energy. So what are we going to do? We're going to find the net work that is done on the object. So in this case, there are two forces. So what we want to do is we want to add up the contributions of how much work each force does and add them all up to get a net work. It's going to be the sum of all works from all of the forces. So what's the work of our applied force? Well, we've done this before. It's just FD. And this will be 10 joules. Now the work of friction force is similar, but it's in the opposite direction. Negative F friction times D. Oh, and we're going to have a friction force. This, if you plug in the numbers, should be equal to 4 newtons. All right. So this will be negative 4 joules. So our kinetic energy, our final kinetic energy is equal to the net work, which will be equal to 6 joules. And what's the final velocity? Well, all we have to do is use our equation. 1/2 mv squared equals 6 joules. To get that v is √6 meters per second. All right, cool. So that's that. And we can move on to potential energy. All right, what is potential energy? Well, to talk about potential energy, we should first talk about what are known as conservative forces. So what are conservative forces? Well, they depend only on the position of the particle. That's an important property. And they also do not depend on the path taken by the particle. So I guess what this is trying to say is the work done by any conservative force is not going to depend on the path that a particle takes. It's only going to depend on the initial and the final location. This will probably be easier if I draw something else. So let's say we have a particle here and we have some force. So our particle travels along a path. It can be any path it wants. And let's say that gravity acts on it. All right, so there's going to be gravity here, so on, so forth. There's going to be gravity everywhere along this path. And even here. But what is the work done by gravity? Well, you can find the work done by gravity. And the funny thing is, you will see that it doesn't depend on which path this particle takes. So as long as it starts right here and ends right here, the work done by gravity will always be the same, or the total work done will be the same. So the particle can go in a straight line, it can go up and then down, or it can go in circles. No matter what, if you take the work done by gravity and add it all up, it will be the same. And we can also show this for springs. And so that leads us to define what we call a potential energy. So potential energy will be some type of energy that a particle has due to its position. What I mean by this is that we can basically define an energy for each position. So going back to our gravity example, let's say we have a block here. Right now it's on the ground, but maybe if it's up here, well, it's higher up. Gravity can do work on it and bring it back to the ground if we drop it. And so what this means is that this block right here is going to have a higher potential energy because it has the potential to convert that potential energy into kinetic energy. That's why it's called potential energy, I guess. So, yeah, there are different types of potential energy for different types of conservative forces. So, the two most common ones are going to be gravity and spring force. Those are mainly the two types of potential energy that you'll see on F equals ma. And the way we define it more formally is that it's the negative of the work done on the object by our force. So if we have gravity in our example here, our force is going to go downwards. So as we carry it up, gravity is going to do negative work, but that will increase our potential gravitational potential energy. And also notice that right here, we have a delta U. This isn't a U, it's a delta U. And why is this? Well, for potential energy, actually what we can do is we can arbitrarily add some constant, and it doesn't really change anything because all of our potential energy has to be defined with respect to some reference point. So in the case of gravity, we find it very convenient to specify the ground as our reference point, or y equals 0, potential energy is 0. And this is because, well, as we go up, potential energy increases. Once we get to the bottom, potential energy is 0. This is easier to work with. All right, but we can just as easily define this location as y equals 0. And now what will happen? Well, the locations below this will have a negative potential energy, and these will have a higher potential energy. But the key observation here is that the difference between the potential energies of any two positions will always stay the same. And that's what we really care about, is the difference in potential energy, because that's what determines how much work is done. All right. And let's talk about conservation of energy. So now with our potential energy, what we can do is say, well, our potential energy, change in potential energy, well, that's negative work. That's what we define potential energy as on our previous slide. But what is work? Well, earlier we said work is the change in kinetic energy. So what is this? This is just the negative of the change in kinetic energy. So what we get is the change in potential energy plus the change in kinetic energy is equal to 0. Or what this is basically saying is that this thing is a constant. So with that in mind, we define it to be the total mechanical energy of our particle. And in a closed system, this is always constant. And this is known as the principle of conservation of energy. So that's, I guess, yeah, this is basically the change in kinetic energy is should be a negative there. Yeah, the change in kinetic energy, I guess their magnitudes are the same, but really there should be a negative sign here. And I guess if it's not a closed system, that's fine. We just have to add in how much work we did to our particle's total energy. So I guess if we do some work, that will increase our total energy. But if otherwise, if we have a closed system, which basically means that there are no external forces, which means that there can't be any external work, that means that the total energy of our system will remain constant. Okay. So now let's talk about some types of potential energy. We have gravitational potential energy, which is the potential energy due to gravity, which I already talked about a bit. And if we go back to our problem a while ago, yeah, this problem. Remember the results from this problem. Number 1 was the work required to compress a spring, half kx squared. And number 2, the work done by gravity is negative mgh. Okay, so now let's go back. And we can see that now we've basically, in that problem, we've derived our formula for gravitational potential energy. We just have the potential energy due to gravity, which is the negative work done by gravity, is mgh. And as I said earlier, h is just relative to some reference point. Right, so if we choose the ground as a reference point, that's very convenient because this will be 0 and it increases as we go up. But we can just easily, so to make this example easier, let's define some sort of coordinate system. So let's call this y equals 0. and that's our current reference point. And let's say this box is at y equals 4. How about that? So what's going to happen to this box is oh, this box is going to start at y equals 4 and fall down until it hits the ground at y equals 0. So what's the change in its potential energy? Well, initially it has mgh, or I guess 4 mg potential energy, and at the bottom it has 0. So what the change in its potential energy is just 4 mg. All right, but now let's say we redefined a reference point to be y equals 1 right here. So now this is our new reference point, y equals 1. Well, what's its initial potential energy now? Well, here, it's going to be a distance of 3. So we have an initial potential energy of 3 mg. But now what's its final potential energy? Well, it's going to be 1 below our reference point. So our final potential energy will be negative mg. And this is also 4 mg. So basically what we have here is that it doesn't really depend where we define our reference point, because that's just going to add a constant to whatever our energy is. And since we don't really care about the actual potential energy, we just care about the difference in potential energy, it doesn't really matter because a constant minus that same constant is going to be 0. And no matter what, the change in potential energy is going to be the same. All right, so we have some examples here. And right now is also 2:30, so it should be time for our break. So I will put these examples up here and you guys can work on them or take your 5-minute break. I will return at 2:35 Pacific time. So yeah. All right, so let's continue. Um, so let me first go over question one, which is we have a block here and it's 2 meters above the ground. So it falls and it hits the ground, and we want to find the kinetic energy when it hits the ground. Well, there are many ways to do this. We know kinematics, but today is about energy, so let's do that. We just learned that the potential energy due to gravity is mgh. So what is its initial energy? Well, its initial energy is its initial kinetic energy plus its initial potential energy. And while initially it's at rest, so it has zero kinetic energy, and it has mgh worth of potential energy. All right. Now, what's its final energy? It's going to be its final kinetic energy plus its final potential energy. Okay, we don't know what its final kinetic energy is yet. That's what we're trying to find. But we do know that after it hits the ground, well, it's at a height of 0. So it has mgh, that's mg times 0, or 0 final potential energy. All right. But now we can use conservation of energy here. So its initial energy is going to be equal to its final energy. And what we get from this is that mgh is its final kinetic energy. All right, cool. And to find its velocity, we've done this before. Mgh is 1/2 mv squared. So our final velocity is square root 2 gh. And you can see that this is the same result that we would have gotten if we used our kinematics formulas, but this is actually quite a bit faster and less calculation. All right. Now, the second example is really a good example of the power of potential energy. So what we have here is a ramp. And the block here. And the ramp is inclined at some angle. I didn't specify, but really it doesn't matter for this problem. And it's at a height of 2 meters. So what I meant by that is that this distance is 2 meters. So it slides down the ramp. And we want to find its kinetic energy at the bottom of the ramp and its final velocity. Well, first of all, let's think a little bit. Our formula for potential energy, gravitational potential energy, it's mgh, right? So all of our points that have the same H will have, and the same M, of course, will have the same potential energy. So if we think about it, this point here, well, it doesn't have to be this point. It can be any point on the ground, and it will have the same potential energy. So the difference in potential energy, it's the same as if the block just fell straight down. So we can use our answer to the previous problem, which was root 2gh. And this is just our answer for the final velocity. And if we had tried to do this with kinematics alone, and actually let's do that. It will be a bit messier. And hopefully after this, you'll see some advantages of when you can use energy instead of kinematics. All right, so this is, let's call this H, and this is theta. And we have a block mass M, and there's also going to be a normal force. So if we remember from last lecture, we gotta have the forces balance on this block, right? So we're going to get that the normal force. Okay, first of all, we will want to tilt our thing so that gravity goes this way. And we're going to have forces cancel out in this direction, in our y direction. So we're going to have our normal force equal to mg cosine theta. And the only force that's left will be our horizontal component of gravity, which is mg sine theta. All right, so we'll get an acceleration of g sine theta. But what is the distance we have to travel? Well, the distance we have to travel, it's going to be h over sine theta. That's just from trigonometry. So we know our acceleration, we know our distance. Let's use a kinematic formula. 1/2 at squared equals our distance, which is h over sine theta. All right. 1/2 g sine theta times t squared equals h over sine theta. We can solve for t. T is going to equal square root 2h over g sine squared theta, or we can write this as root 2h over g times 1 over sine theta. And our final velocity is then just at. We multiply this by our acceleration, which is g sine theta, and we will get root 2gh, which is the same as here, as expected. So really, here we can see how conservation of energy gives us the same answer, but it's much faster. We don't have to worry about all the angles, or we just need to know what the total difference in height is for our particle. All right. Let's go on to a more challenging problem now. This is from the F equals MA. And I do have a walkthrough for this. Hold on. Okay, so let's first explain the problem. Okay, we have a block of mass 3 kilograms, and it's sliding down one ramp and up a second ramp. And both of the ramps are inclined at 30 degrees. All right, what does this look like? So we have one ramp here and another ramp here. And this is 30 degrees, and this is also 30 degrees. So our mass here, it goes down this ramp and then up this ramp. Okay, but there's also going to be friction. So friction is going to act against our blocks the entire way. All right, so the block begins at a height here. This is 1 meter. And we want to find the final height of the block on the second ramp. Let's call this H2. So this is like H1 is 1 meter. We want to find H2. All right. So, okay, let's do step 1 first. So what is the block's initial energy? I'll give you like 1 minute to do this. Shouldn't be too hard. All right, yeah. So, how to do this? Uh, let's first of all make the problem a bit smaller so I have more space to work. All right, cool. So first we want to find the block's initial energy. So what will this be? Well, let's also enlarge to draw a better diagram. So we have here initially it's right here. And it's at a height of 1 meter. And it starts out at rest. So what for initial energy, yeah, our initial energy, it has 0 kinetic energy. And it has mgh of potential energy. This is just mgh. And this works out to be around 2930 joules. 29, close enough. All right. And the second step is, okay, the block reaches here, it gets some energy, and then it will start to go up the second plane. And it will stop Well, there's going to be conservation of energy, so it won't go quite as high as the first time, but it will stop at some height h2 here. Um, okay, so the second part of our walkthrough is to find how much total distance it travels. So basically what that's asking is what is this distance plus this distance in terms of our h1 and h2. So the reason why we want this distance is, of course, then we can do work is force times distance. So we're going to want to find the work of friction. But for now, just I'll give you like another minute or two. Is find the distance in terms of h2, and this should be just geometry, I think. Okay, so it's been a few minutes, so let's talk about this. Um, we want to find the total distance it travels. And what we have here, oop, we have two triangles basically. We have an angle, they're both 30, 60, 90 triangles. And we know this length is h1. So what is this length? Well, this length is just h1 divided by sine theta. This will happen to work out to 2h1 because sine 30 should be half. Okay, now for a second triangle, we have the same thing. This is 30 degrees. Now this is h2, and this distance will be h2 over sine 30, which is 2h2. So the total distance that the particle travels is just 2h1 plus 2h2. Cool. Now, let's go on to the third step of our walkthrough, which is to find the friction force on the block. So this will require some content from our previous lectures, but just draw force diagrams, and I think I went over this many times in my previous lecture. So yeah, just find the force of friction on the block in terms of m, g, mu, whatever you need. And I'll give you a few more minutes for this one as well. Oh, it's been a few minutes. Um, First of all, let me clear this up. So for number one, we got that the initial energy is mgh. And for number two, we got that the distance is 2h1 plus 2h2. Okay. Now we want to find the force of friction on the block. And okay, so let's start out by drawing a picture and a force diagram. So we have our block here. There's going to be three forces on it. There's going to be the gravity force, the normal force, and a friction force. Okay. So again, we define this as our x-axis and this as our y-axis. So in the y direction, well, first of all, this angle here is theta. And so in the y direction, our two forces are the normal force and the y component of our gravity force, which is just mg cosine theta. And those have to balance out because the block can't accelerate into our incline. That just doesn't happen. So what we get is our normal force is going to be mg cosine theta. All right. And now all we have to do is get that friction force is mu k times the normal force. And so this is going to be mu k mg cosine theta. All right, so that's our friction force. Now, for the fourth part of our walkthrough, find the work done by friction in terms of H2 and H1, I guess, also we're using. So this shouldn't be too hard. I'll give you a few minutes to think about this. And as always, if you have any questions, don't hesitate to ask me, or once you're done, send me your answers in chat. All right. It's been a few minutes, so let's talk about this. Um, all right. So what's going on here? Well, the friction force is always going to be opposite to our object's displacement. So while it's going down this plane, friction's going to be that way. And later on, when we're going up this plane, friction's going to be that way. So what's going to happen? All we need to do to find the work done by friction is just work equals negative because opposite directions. Um, work equals negative force times distance. We know our friction force, it's mu k mg cosine theta, and we know our distance. That's the distance we found in part 2. So this is the work done by friction. All right. Now, let's find the block's final energy in terms of H2. In the interest of time, I think I will just finish off the remainder of the problem. So what's going to happen by work energy theorem? Well, the final energy is just going to change by however much our work is, right? Work is going to be the change in our energy. So that means that our final energy is going to be our initial energy plus our work. Well, we know our initial energy, it's mgh1 here, and we know our work, that's negative mu k mg cosine theta times 2h1 plus 2h2. All right. That is our final energy. But oh, but this is also equal to mgh2. Why is that? Because again, it's at rest. And also, so all of its final energy is in potential energy. So we can also write this as mgh2. All right, so now we have one equation. Our only unknown here is h2. So we can solve it. And we should get something like, oop. Let's just solve it really quickly here. mgh1 minus, ooh, 2h1 mu k mg cosine theta minus 2h2 mu k mg cosine theta equals mgh2. Move all of the h2s to one side. 2h1 mu k g cosine theta. We'll have on this side h2 times mg plus 2 mu k mg cosine theta. And we should get that h2 is equal to, let me go up a bit. We should get that h2 is equal to, if we divide both sides by mg and then just divide out, we should get h1 minus 2h1 mu k cosine theta divided by 1 plus 2 mu k cosine theta. All right. And I think what this works out to, let me double check. I wrote it down somewhere. This, if you plug everything back in, this should work out to 0.18 meters. So that is our final answer. All right, let's move on. Let's talk about elastic potential energy. So, as I mentioned earlier, this is the energy due to springs. And like we did in our earlier problem, we can easily show that our spring potential energy is going to be equal to 1/2 kx squared, where k is the spring constant and x is how much you stretch it. All right. So let's go on to another challenge problem. And I also have a walkthrough here. So let's just start with part 1, which is we want to find the initial energy of the system. And right, actually, first let's describe the problem. What is our problem here? We have a block has mass m, and there's a spring here with spring constant k. And initially, the spring is not stretched, and the m is some height above the ground, and it is moving downwards with a velocity of v. All right, so find the initial energy of the system. And also, just a quick note, in this problem, it's actually easier to make the potential energy for gravity because there's going to be both gravity and spring potential energies. It will be the easiest to set this initial distance as y equals 0. So this will be our reference point. And you will find that this makes the calculations much easier. All right, so I'll give you a few minutes to do this. As always, you can ask any questions you have and just send a message to me or send me your answers once you're done. Okay, so this actually might be easier than it seems. What we're just trying to do is find the initial energy, which is going to be the kinetic energy plus the potential energy. So what's its kinetic energy? Well, 1/2 mv squared. That's just the kinetic energy. And the potential energy, well, there's mgy potential energy, but it's at y=0. So this is just 0. And there's 1/2 ky squared spring potential energy. Hold on, let me move this over. There's 1/2 ky squared spring potential energy. But this is also equal to 0 because y is still 0. So what we end up getting is that the initial energy, this is just 1/2 mv squared. All right. Let's move to step 2. Express the potential energy of the system in terms of the spring's displacement. And this shouldn't be too hard either. I'll give you a few minutes to think about this. Yeah, okay. So I've actually already written this down. So the spring, if the spring has some displacement y, and this is its initial y=0, what's its potential energy? Well, it's going to be 1/2 ky squared. That's from the spring. And it's going to have an additional mgy from gravity. All right, so this is just our expression for the potential energy. Okay, and now we can move on to step 3 of the walkthrough. So the observation here is that we want to find the maximum speed of the block, right? But what this really means is if v is maximum, that also means that its kinetic energy is also at a maximum, because 1/2 mv squared will also be at a maximum. So we want to maximize its kinetic energy. Well, what does this mean for the potential energy? Well, the kinetic energy plus the potential energy, it's a constant, right? So if the kinetic energy is at a maximum, this means that the potential energy must be at a minimum. All right. With that in mind, we can proceed to solve the problem. So let's think. We have our potential energy, 1/2 ky squared plus mgy. And we want to minimize this. Some of you might know how to complete the square or take the derivative and set it to 0, or whatever method you use. You should get that it's minimized when y is equal to negative mg over k. All right. So now that we know this, we get our minimum potential energy. We can plug this back in, 1/2 k, and then here we'll have negative mg over k, and that's squared, plus mg times negative mg over k. And this will simplify to negative 1/2 m squared g squared divided by k. All right. Ooh, probably do this. Okay. Now we have our minimum potential energy. Let's find our kinetic energy. So we got our initial energy, that's just 1/2 mv squared. And this is equal to our maximum kinetic energy plus our minimum potential energy. So this will be 1/2 mv max squared minus 1/2 m squared g squared divided by k. All right, we can cancel out a 1/2 m and then isolate v max on one side, and we'll get v max squared will be equal to v squared plus mg squared over k. So our final answer is that the maximum velocity equals to the square root v squared plus mg squared divided by k. This is our final answer. All right, with that, we are exactly on time. So thank you for listening. If you want some extra practice, you can find more problems on those pages of Morin's book. And if you have any questions, you can ask me. Other than that, if you have any questions later on, you can also join the Discord and ask them there. And with that, thank you for listening, and I'll see you in the next lecture.